So as we get into Module 6 here, we'll start with Module 6.1. We're looking at material from Chapter 4 for pure bending, particularly looking at deformations, composite materials, and stress concentrations. So within this module here, we're going to take a look at the general principles of bending behavior, talk about the deformations, strains, and normal stresses in beams that are subject to the pure bending. Then we're going to describe the behavior of composite beams made of more than one material. From there, we're going to review the stress concentrations and how they're going to be included in the design of beams. So within this module, we'll talk about the theory, some of our governing equations, some practical applications to apply these equations in theory, and then go through some problem solving. So as we get started, we're going to take a look at pure bending. What is pure bending as we jump into Chapter 4 in our textbook here? Well, pure bending is prismatic members subjected to equal and opposite couples acting in the same longitudinal plane. So we can see over here we have a diagram that we develop from an image right here. So if we want to take a look at this right here, and we want to take a look at the free body diagram for this barbell right here, as this Olympic lifter lands in the bottom of a snatch right there, we can see, well, he's got these two forces from his hands right there and right there, and then we've got these distributed loads that we're just going to kind of point load acting in the bar right there and right there. Now this is a simplification because technically the hand has a width to it and these weights have a width to it there and it'd be a distributed load. But for simplicity's sake, let's just say that these are point loads at those four positions right there, which puts that barbell into 4-point bending. Now this is an important problem to consider right here, especially from a design application right here. We're talking about the material of the barbell. When we get into some of these more complex barbells, there's a lot of engineering that goes into it. Some of the companies like Rogue really have put a lot of different things. We're talking about composite materials actually as we get into some of these barbells and different materials on the end and different bearings for how the weights will spin, and it becomes a very, very complex problem very quickly for something as simple as a barbell. But let's just take a look at a simplistic view of this here. We'll consider one material. We're just going to look at it as a free body diagram right there with 4-point bending for point loads right there. So that's what we have here in part A. We have a free body diagram of the barbell pictured again in the beginning of this chapter from our textbook right there. So we can see that down there. Again, okay, there's our two loads right here. Let's just say that those are 80 pounds on each side. Those are 40-pound plates each, so we have 80 pounds there and 80 pounds right there. And then we can see down here we have our R sub C right here, which is, and our R sub D right there, which is our reactionary forces where load coming up, where the lifter is actually holding the barbell. So a couple other things to consider. Again, with a lot of these diagrams, a lot of these problems, we're doing a lot of assumptions and simplifications. The other thing that we haven't done is the weight and the distributed load of the barbell itself. So with this right here, we're really not talking about anything except the external loads right there, not how the weight of the barbell is distributed, and the fact that the center of this is going to be a different composite structure than the outsides over here, and the weight distribution is going to be different than that there. So again, as we go further and further and make this more of a realistic problem, those are things to consider. But again, we'll just go with the simplistic case here, 4-point bending. A and B are the two loads from the plates. C and D are the reactionary loads right there where the lifter is holding it up like that, which puts that bar into a bending moment, 4-point bending right there. So we can see down here we have a part B right here. We have a free body diagram of the center bar portion showing pure bending. So we're only looking at the center bar portion right there for pure bending right there. So if we did out our calculations right there, we could find our moments from the free body diagram right there, our forces times our perpendicular distance right there. So we can see, okay, 80 times 12 right there. And you have these guys acting right there. So we can figure out our bending moments based upon all that information for the bar right there. Do this out. This is something we would actually want to do on our free body diagram, summation of forces, summation of moments, double check all of our distances right there. And then when we actually do that out in a problem statement, we could find the values for those bending moments. So now I want to talk about some other types of loading. In particular, I want to take a look at eccentric loading, transverse loading, and the principle of superposition. Now, if we're dealing with eccentric loading here, axial loading that does not pass through the section centroid produces internal forces that are equivalent to an axial force and a couple. Now, if we're dealing with transverse loading, what we're talking about here is concentrated or distributed transverse load produces internal forces equivalent to a shear force or a couple. And as we move on to the principle of superposition, the normal stress due to pure bending may be combined with normal stress due to axial loading and shear stress, which is going to be due to shear loading, to find the complete state of stress with that there. So that's the benefit of that principle of superposition down there, is that we can find the complete state of stress. Now, if we take a look over here at the figure on the top left, we can see we have a clamp there. So what figure A part A of this figure shows is that the equal and opposite forces exerted by the lumbar on the clamp. So there right there, you see these equal and opposite forces, P prime and P, that are exerted by the lumbar on the clamp. Now these forces are going to result in the eccentric loading of the straight portion of the clamp. So this is our straight portion of the clamp over here. This is eccentric loading again. Axial loading that does not pass through the section centroid produces an internal force equivalent to the axial force and a couple. So that's exactly what we're dealing with here. As we can see that, there we go, does not pass through the centroid section of that clamp right there. So therefore we're dealing with this eccentric loading. So now that we know we're dealing with eccentric loading, we can come over here to part B right here, where it's the free body diagram of the upper portion of the clamp right there. And we look at that, we can see this section CC. This has passed through the clamp, and a free body diagram has been drawn right there that's showing the upper half of the clamp. So that's what we have going on right here, the section CC, the upper half of the clamp right there. Now we can take a look at those internal forces now that we've created that section there. So internal forces in the section are equivalent to the 150-pound axial tensile force. So that's exactly what we said. Force is equivalent to an axial force for eccentric loading right there. So we can see the 150 and the 150 right there. And we have a moment right here now of 750 pound-inches right there. And there's our moment right there, 750 pound-inches. And again, we can do out our summation of forces in equilibrium right there, and we can show our force times the perpendicular distance in order to get our 750. Which quickly we can just look and see this is the 5 times the 150, our force times our perpendicular distance gives us that moment about that point right there, if we're doing about that point right there where our moment is. So 5 times our 150 gives us that 750 right there for our 750 pound-inch couple M. So now we'll take a look at this diagram here. What we want to consider in this here, we can take a look up here at part A. We have a cantilever beam with end loading, so we're consider this cantilever beam supporting a concentrated load P at its free end. There's our concentrated load P right there. We can see that's a distance L from our fixed support right over here at point B. And then what we can see, if a section is passed through at C, so where is our section passed through at C right there, at some distance X. This is measured from A, which is the end point over here. So this is the distance X that we're talking about right there, as we can see down here. What we can see is that this shows the internal forces in the section consistent of a force P prime, which is equal and opposite to P. So there's our P prime right there at section C. We take that section, equal and opposite to our P right there. And now we have a couple moment of the magnitude of P times this distance X. So there's where we're going to see this moment right there around that point there. So as we see, this is a concentrated or distributed load, transverse load, to produce internal forces equivalent to a shear force in a couple. So that's what we have going on in this case here. So next we're going to take a look at a symmetric member in pure bending right here. So we have over here, we want to note is that the internal forces of any cross section are equivalent to a couple. Now the moment of the couple is what's known as the section bending moment right there. Now from statics, we can recall that a couple M consists of 2 equal and opposite forces, and that the sum of the components of those forces in any direction is going to be equal to 0. Now this moment is going to be the same about any axis perpendicular to the plane of the couple and 0 about the axis contained in the plane. So if we take a look at figure 4.5 up here in part A, we can see we have a member in a state of pure bending right there. So we see our 2 moments right there acting at A and again at B right there. So again, this is a member in the state of pure bending. Now over here in B, you can see we've sectioned it right here. We're taking a look at it as C right here. So that's what we have over here is a C right there. We see that any intermediate portion of this whole AB member right here will also be in pure bending. We see there's our moment M prime and our moment M right there. So that's in pure bending as well. Now all these requirements we just discussed, these can be applied to the sums of the components and the moments of the statically indeterminate elementary internal forces. So now if we look at the internal forces, we have these following relationships down here. We're talking about our forces in our x direction. We can reference back up to our figure 4.6 here. We see, okay, we have our x direction here. We have our y direction going up like that. We do our right hand rule out, and there's our z direction going positive over here. So we can say the forces in our x direction are equal to the summation of our stresses in the x direction, sigma sub x, times dA. And these are equal to 0. It's an equilibrium. So we go back up to our figure 4.6 right here to our diagram right there, and there's our sigma x dot dA right there. So that's, if we sum all of those in that direction there, and that's the summation of forces in our x direction equal to 0. Now we can say we also have our moments in the y direction, moments in the z direction right there, and these are equal to, we say it's force times perpendicular distance right there. So if we look and take our force in our x direction, that was our x times dA times our z right there for the perpendicular distance like that, and that'll give us our moments about y right there, and our moments about z are the integral of negative, again, make sure you pay attention to your sign convention, of your y times our sigma y dA is equal to our moment right there. And that moment is this moment right here. We can see on the right-hand side over there. So what this is saying is the summation of the infinitesimal stress elements must produce the equivalent bending moments. That's why this is not equal to 0 right there. This is equal to our m right there. So we take a look at that and we can go through, okay, there's our y right there. There is our sigma dA right there. So we multiply those two together, take the integral of those, and there is what we get over here on our right-hand side, showing the equivalent pure bending moment. So next we're going to take a look at bending deformations. So we're talking about beams right here. So beams with a plane of symmetry in pure bending are what we're dealing with here, which is a simplified case. So within this case right here, what we can say is that members are going to remain symmetric, and that as the member bends uniformly to a circular arc. So we can see this illustrated over here because it bends uniformly into the circular arc over there. Now also we can see that the cross-sectional plane passes through the arc center and remains planar. Now, if we look in closely up here at the top, going from A to B right there, we can see that the length of the top is going to decrease. So as we bend this in, we move this in like this, and again, imagine we're actually physically coming up here and bending this member like that, bending that beam. What's going to happen? Well, that top surface right here, that length from A to B, is going to decrease, whereas the length at the bottom from A prime to B prime, that's actually going to increase. You can take and physically bend it, and you can see those top ones are going to move in, get shorter, and the bottom one here is going to lengthen. Now, a thing to note that a neutral surface, now this neutral surface is parallel to the upper and lower surfaces, and for which the length must not change. So this must exist. In fact, there must be a neutral surface in here that does not change in length. So we're going to use that as kind of a line to determine what things are going to get shorter, what things are going to get longer. So stresses and strains are negative. They're compressive. You think of the top of this here, when they're above that neutral plane. But they're going to be positive, and they're going to be in tension as they're below that neutral plane. So the neutral plane is going to be kind of our limit there, where, again, that length doesn't change, and above it, it goes in compression, and below it goes into tension there. And you think about that, you're compressing all these top elements right there, but you're stretching and putting all these elements right there into tension. So we're going to use this neutral surface in a couple of other applications as well. So it comes back into play when we're talking about the strain due to bending right here. So if we consider a beam segment of length L, well, after deformation, the length of that neutral surface is still going to be L. That's the definition of a neutral surface. It doesn't change in length. But there are going to be some other things occurring at other sections other than at that neutral surface, and here's how they're going to vary based upon some information, some geometry related back to that neutral surface or our neutral axis there. So we can say this is our neutral axis right here. If we're looking this at part B as our transverse section at the origin right there. There's our origin right there. We can see our neutral axis coming straight across like this here. Now if we go over to part A where we're looking at the longitudinal vertical view of this right here, you can see right there from D to E coming across the origin right there, that curved line, which I'm going to try to trace right there, that right there is going to be our neutral axis right there. So now if we're talking about our L prime, our new length right here, we can say this is equal to rho minus y times our theta. Well, we can see our rho minus y is right here, where rho right here is the distance from C down to that neutral axis right there, and y is that difference right there. So now we can see if we're going up to some point of interest right there. There's our y, that distance up that we're interested in, that much further up our segment right there. So this is equal to that times our theta, which this is our theta right here. That angle after it bends right there is our theta term. Now our delta is going to be the deformed length minus the original length right there. So L prime minus L. So now we have a value up here above for our L prime, so we can plug this L prime in right here, right there, my rho minus y times theta, so that's what I do, I plug that in for that there, and then I also have a value for my L over here, and that's just my rho times theta right here, where it's this rho times this theta right here is my L. So that's our L and our L prime right there. So next we want to find our strain. So let's take a look at our strain in the x direction right here. Well, our basic definition equation for strain is our delta over L right there. So now we have a relationship for delta up top there, and we simplify that down. That simply becomes our negative y theta right there. So we have our negative y theta over L. We have a definition for L again. That's that rho theta right there. We can plug that in right here now, and we reduce this down, simplify. We can see our thetas cancel right there, and what we're left with is that we have our epsilon, or our strain in our x direction, is equal to negative y over our rho value there. So again, this is our y value right there. This is our rho value right there. And this tells us that strain is going to vary linearly. Now we can get our strain, our epsilon sub m right here is equal to c over rho right there. We can come back over, get those variables off here. We can see this is our distance c right there from the top surface down to that neutral axis right there. So this will be our max strain right there. This is over our rho value right there. So there's our rho going from this point here at the top of the angle there down to our neutral axis right there. That's our rho value there. We could rearrange that and solve for that rho value if we needed to get that value there. And that's just saying that is equal to that distance c right there from that top surface down to our neutral axis divided by our max strain right there. We can also get a value now here for our strain in the x direction right here relative to our max strain right there. So we go back up to the top of that there. We can say that this is equal to our strain in the x direction is equal to negative y over c now rather than y over p, because we've subbed this in for this and rearranged some variables times this epsilon sub m right there to get this relationship. So now that we've looked at strain from bending, let's take a look now at stress due to bending. So for an elastic, a linear elastic and homogeneous material, a simple case right there, we can relate back to equation 4.11 in our textbook. We're going to see that our sigma sub x is equal to our modular elasticity times our strain in that x direction. We can plug in some values that we've seen for that strain value right there, and we replace that. Now we have a negative y over c right there times that epsilon times our E sub m right there. Or again, where that is our max strain right there. Now from that, we can rearrange a little bit more to see that our stress varies linearly right here. See that this is equal to, when we reduce this down a little bit more, we can see that y, negative y over c times our sigma sub m right there. So if that's our sigma sub m right there, our sigma sub m is the maximum absolute value of our stress. So that comes from equation 4.12 in our textbook. If we go over here to figure 411, we can see the bending stress stresses that vary linearly with the distance from the neutral axis right there. So here's our neutral axis going right down the center. There's our x value right there. We can see that these vary linearly as we go above and below it, where there's compression or tension right there. And we can see up here, coming off the end of this right here, there's that sigma max. That's the maximum absolute value of the stress right there. And that's that distance from where that linearity, the stress right there from that linear distance right there from our neutral axis is at the max at that outer surface right there, and that distance from the neutral axis to the outside surface right there where that stress is the max right there is this value, this distance value of c right here. Now for static equilibrium, we can see down over here what we have is our f of x is equal to 0 right here, which is the integral of our sigma x, or stress in the x direction, dA. Again, we recalled that from before. That's our definition for our value for our force in the x direction. So take the integral of that is equal to the integral, and we plug in now. We have a value for sigma sum x up here. So we have this relationship right here, which we can then plug in this relationship for right there. So we can take that, plug that in down here now for our sigma x. So we have now our integral from negative y over c times our sigma m, or again, that sigma m is the maximum absolute value of the stress, times dA right there. So therefore, 0, so fx equals 0, is equal to our negative. We can rearrange this a little bit, pull out our constants out front, our sigma m over c times the integral of y dA. And this goes back to equation 4.14 in our textbook. So looking at some other equations related for static equilibrium, so we go through that there. We can go back to equation 4.3 where we have our moment is equal to, when we do some substitutions right here, the integral of our negative y sigma x dA. Plug into this right here, so we can see, okay, this is our negative y right there. Now we have our sigma x right there, which we can go back up to this relationship in 411 and 4112, say that this moment is equal to the integral of negative y times now our negative y over c times our sigma m, or that maximum absolute value for our stress right there, dA, when we plug into that guy there. Now we can pull some things out that are constants, and we end up with our relationship we see in equation 4.14. So moment is now equal to that sigma sub m, that maximum absolute stress value right there, over our value of c, and we can see again that's our c right up there if we go back to our diagram, times our integral of y squared dA So then we can go through this, do a couple more substitutions, and we can see, okay, this is going to be equal to our sigma m times our I over c right there when we do our integral. So we reduce that down. We can see now we have m, our moment, is equal to our sigma m times our I right there, moment of inertia right there, divided by that distance c right there. So therefore we have this relationship shown here in equation 4.15, where sigma sub m is equal to m c over I right there, where we can replace this here for our c over I right there with this value of s on the bottom on our denominator right there. And then we can sub in this relationship here, that sigma x is equal to y over c times our sigma m right there for that max value right there. Plug that back in there, and we can finally come up with our final solution. We see over here the relationship from equation 4.16 in our textbook, that sigma sub x is equal to negative my over I. So now this is interesting to see, and I would definitely recommend going back through and go through the details of steps along the way. But it's important to know how we derive these equations, starting from our basic equations, plugging them all in and seeing how we come up with these again, rather than just plugging blindly into this relationship here. Understanding where it came from and how we got there is important, because yes, this may work for one certain equation that we're working on for a homework problem, exam problem, or example problem we're working through, but we may need it slightly different for something else. So the understanding the derivation that we're going through with all these other governing equations becomes very important. Couple things that we can draw from what we've seen here within these governing equations right here is that the first moment with respect to the neutral axis is going to be equal to 0. Therefore, if that's the case, then the neutral axis must pass through the section centroid right there. So those are a couple of key things to keep in mind as we're working through these problems. So that leads us into discussion now of beam section properties. So if we take a look at equation 4.15 in our textbook right here, we can see the maximum normal stress due to bending is given by the relationship here that our sigma m, our maximum normal stress, is equal to mc over I, where m is our moment, c is that distance from our neutral axis up to the outer surface there, and I is our section moment of inertia. Now we also have this relationship here now that we can bring in now that we saw previously on the last slide there, this s value. This s is our section modulus here, and this is equal to I over c, again, where I is that section moment of inertia right there, and c is that distance to the outer surface. So we can plug that in there, and then 4.15 comes down to sigma m is equal to m over s when we plug in that s is equal to I over c there. Now if we take a look at that relationship now in 4.15, what this lets us know shows us that the beam section with a larger sectional modulus, or our S value right there, so if we look at this, if our S value is bigger on the denominator right there, what is that going to do our value for our sigma sub m? Well, that's going to make that our sigma sub m be lower. So if we increase the value of S, it's going to decrease the value of sigma sub m, so they're inversely proportional right there. So let's go ahead and now consider a specific case here where we're dealing with a rectangular beam cross section. So we can take a look over here at figure 4.12. We can say an example here for a rectangular beam cross section. In this case here, it's wood right there. So now this leads us into our equation 4.19 in our textbook right here, where again we have this S value here for our section modulus. Now this is equal to I over C right there. So from equation 4.19, we have that relationship there, where now I, again, being our section moment of inertia right here, we can plug in a value for the specific case here of a rectangular beam cross-section. We can go back to our appendices and some of our previous courses and textbooks there, and you look up tables for different shapes and geometries. So for a rectangular beam cross-section here, we see that our I value here, or our moment of inertia value there, is 1/12 BH cubed. Now our C value right here, this is going to be half. It's going to be the radius, the distance from that neutral axis out. So our neutral axis is in the middle of that right there. So half our diameter, or our H value right here. So it'll be half of that, and this will be H over 2. So we can do out some math manipulation here, and we say 1/12 there and a 2 there. That becomes 1/6. A BH cubed and a H on the bottom can cancel out there. And what we end up with is just an H squared. Well, our H squared right there, that could be our area right there. Our base times our area, a base times the height is our area right there, leaving us with one more H right there, so we can reduce that down to 1/6, the area, which is base times height, times our H value right there. Now what we can also see though is that this H value here means it's not just the cross-sectional area, but the shape of the cross-sectional area that is going to come into play when we're talking about this here, because you have that extra H value there when you're considering the sectional modulus here, which again ties back in now to our sigma sub m up here. So between two beams with the same cross-sectional area right here, which we can look in equation or figure 4.12, we have that 6 times 4 is 24 inches squared, and 3 times 8 is 24 inches squared. So they both have that same cross-sectional area. But the beam with the larger depth, the bigger H value over here, in this case here, our H is equal to 8 compared to our H is equal to 6 right here, will be more effective at resisting bending right there. And that goes back, if we plug that value back in here, you can see that H value is going to be larger there. So we can go up there, and that makes, if our H value is larger there, that makes our S value larger. Now if our S value is larger here, it makes our sigma sub m smaller, so it's going to be less stress right there, so resisting the bending right there. So that is a good way to take a look, and why it's important to look back at how we develop these equations and understand what each of the variables mean, how they relate to our diagrams right here, and we can get practical answers to questions like that from just looking at our governing equations. So that leads into some practical development application here of I-beams right here. So there's two types of steel beams with cross sections here. We have an S-beam and a W-beam there, and you can see what this does right here is this shape, this geometry here, what it does is it then increases that H value. So a larger depth, a larger H value right there means it's going to be more effective at resisting bending. So that's why these I-beams that you can use in construction a lot of times to resist that bending. They're going to maintain that shape. They're not going to bend as much because this H value is a lot larger. And again, we call from our neutral axis right there, our H over 2 is that C value right there as well. So with that value right there, we can see with that larger H, this is going to be better at resisting bending. So the shape of these different types of I-beams is going to come into play and be very useful for that application. So dealing with these shapes right here and these different geometries we just discussed in those beams, we can reference back to Appendix C in our textbook here for the properties of rolled steel shapes right there. So we're dealing with these American standard shapes, or our S shapes right here. We can look up the properties of these shapes right there. Now we have a general diagram up top right here. We can see that total height right here. They're calling D within this here. And you can see of the flange up top here, the little lip up there, that's a T sub F right there. Then we have our X-axis and our Y-axis going down. The neutral axis is there. And we can see down here we have our B sub F for that distance right there, and we have our thickness here of T sub W. So again, this is something to take note of. Not every table, not every textbook, not every resource is going to use the same variable. So having a diagram like this is very nice and useful, because then we can see, okay, well, they're calling this D, but I call it H. Or they're calling this T sub F and I call it a T sub H or something like that. Whatever it may be, but understanding what those values are, what those dimensions are, and how they relate is important. Then we can come back down here to this chart down here from the back of our book in Appendix C down here, and we can see, okay, for this type of designation right here, what is our area, what is our depth value, what is the flange right here, there's our width thickness, our T sub W right there, so we can see all those. There's our B sub F value that relates to our B sub F values there. There's our T sub W value, there's our T sub W value there, our T sub F comes up to our T sub F up here. So we have all these values, and we can back out all this information right here, our IX, our SX, and are we dealing with our X-axis going across this way, or are we going the other way right here down our Y-axis, and we can get our I sub Y values there. And also pay attention to these guys right here for our units as well. So the next section we're going to take a look at here is deformation in transverse cross sections right here. So we can see over here we have in our diagram in figure 4.16 deformation of a transverse cross section. So we can see there's our neutral surface right there, and we can see the neutral axis of the transverse section right there with the red dotted line going right through the center of that there. We can see there's our value for C. Here's our rho value right there. We could get our angle off of this right there if we needed it as well. So then we have all this down here. Now what we can see from our distance down here at C prime, we have going up to our neutral axis right there, we have this distance along this line here that we have as our rho prime is equal to rho over V right there. So this relates back now. So what we can see from this information given on this diagram here, the deformation due to bending moment M is quantified by the curvature of the neutral surface. So this rho gives us the information on the curvature. So we look at the inverse property of that. We have that run over rho is equal to our epsilon m, our max strain right there, over that value of C. So again, that C is the distance to from our out to our outer surface right there. And this is equal to, we've done some of the other relationships and equations there. This is going to be equal to our sigma m over our E sub C value there from some of the previous relationships we talked about earlier in the module there. We can then reduce this down right here and say, oh, let's pull this apart right there, and we'll take this as two separate parts. We'll go 1 over EC, and then we can do this relationship over here where we now have that our sigma sub m is equal to our MC over I from the previous relationships there. We can look at that, and then what we see when we multiply these through together, we have the relationship here that 1 over rho is equal to our moment m over the modular elasticity times our I value right there. So now relating back to our textbook, this is equation 4.20 in our text. We have our 1 over rho is equal to our epsilon sub m over c right there. We do these conversions from other relationships, and we end up with this m over ei, which is relating back to our textbook here, equation 4.21. Now, something to think about with this relationship here is although transverse cross-sectional planes remain planar when subjected to the bending moments, in-plane deformations, so we're looking at the in-plane deformations, these are going to be non-zero. So now we have the set of equations right here for epsilon sub y and epsilon sub z right here from relationship shown in equation 4.22 in our textbook right here. We have the negative Poisson's ratio times that epsilon sub x is equal to, we have a relation for epsilon sub x of y over p, plug that in. So our epsilon sub y is equal to our Poisson's ratio times y all over our value for rho right there. And the same for z, this is equal to negative Poisson's ratio times e sub x, which again we plug back in there for our y over rho right there. So our y over rho or our Poisson's times y over rho is equal to our epsilon sub z. So from equation 4.22, for this particular case right here, our epsilon sub y is equal to our epsilon sub z. So this lets us know that there's expansion occurring above the neutral surface and contraction below it, which cause an in-plane curvature. Now this leaves us, when we're talking about curvature right there, we have this relationship shown here in equation 4.23 in our textbook. We have 1 over rho prime right here, which is equal to Poisson's ratio over rho. And this is equal to an anti-clastic curvature is what we're calling that right there from equation 4.23 in our textbook. So now that we've had the opportunity to look through some bending relationships for beams of single materials, what I want to do next is take a look at bending members made of several different materials right here. So let's consider the fact here that we have in figure 4.19, consider a bar consisting of two different materials, E1 and E2 right there. So now the normal strain is going to vary linearly with that distance y. So we can see right here, there's our distance y, there's our y-axis right there, which is again why it's very important that we label our axes clearly for these types of problems there. We can see that it does vary linearly down along that there. And we can see that relationship that it varies with, our epsilon sub x right here, the strain, in our x direction, is equal to negative y over that rho value there. And this comes back from the beginning of this chapter here, where we're looking at equation 4.8. So what we can notice with the difference here now that we're dealing with a composite, two different materials right here as compared to one material, if we look over here again at figure 4.19, we can see in part A where our neutral axis is, and this neutral axis is shifted from the centroid. So rather than being right in the center of it like we're used to with one type of material, it's now shifted because we have two different types of material. We have a composite member. So when we look back up here at the interface between those two materials, we draw that dotted line right across right there, we can see this is no longer where our neutral axis is right there. So when we're looking at our strain right here, we just said it varies linear with that distance y. We can see this still intersects and goes at 0 right there at down our neutral axis and not at the interface of the two materials. So that's something to make note of. Thus, we say that this neutral axis does not pass through the section centroid of the composite section. It's down here below, for this case here, where this neutral axis is shown here down through the second material and not in between both of them. Now, what we want to do is deal with this piecewise, individuals, just like any of the other problems we've done before, deal with each individual separately. So we take here and we'll call this piecewise linear normal stress variation right there. So we'll have a sigma 1 and a sigma 2. And these relationships are found from equation 4.24 in our textbook. So we're talking about sigma 1 right here. This is for the top material, material number 1 right there. So this says that sigma 1 is equal to our modular elasticity, whatever that material is, times our strain in the x direction there. Now this is equal, then we can do our substitution right there for our strain right there is our y over our rho value right there. And this is a epsilon 1 right there for material 1. And we do the same thing for material 2 on the bottom here. And we say sigma 2 is equal to this value now here of our modular elasticity for that material times our epsilon in the x, our strain in the x direction right there. And this is equal now to our negative E2 over our y rho right there when we do that conversion for our epsilon x is equal to that negative y over rho there. So now we have a relationship, and we clearly drawn this out in section C over here for sigma 1 and for sigma 2 for the two different materials related to our modular elasticity of each of those two different materials, which makes sense. So going back over here, what we can take a look at now here is there's a way that we can geometrically look at this as if it were one material but change the geometry of it right here. So if we're talking about that, what we saw in part A up top here, we can redraw that down here. It has some width B right there, and then the bottom has that same width B right there. Well, we can change this bottom shape of the bottom material here and call it simulate it as one type of material right here, where some factor right here, n right there, where this is now all going to be considered one material right there. And having this geometry, we have some n's of b at the bottom. We still have that b at the top right here. So this is a transform section based on stiffness, again, right there. So that's our modular elasticity, our E value right there. And this is used to calculate our neutral axis. So within that, we can take a look at some of these elemental forces that we're looking at here. So we have our dA, some little elemental area right there. So we can take a look, if we're going to look at our elemental forces based on that elemental area dA right there, we can use these relationships right here from 4.25 through 4.27 in our textbook right there. So if we go to 4.25, we can say this force dF1, the elemental force right there, for the for 1 is equal to our sigma 1 times our dA right there. So again, that's the same way we're doing our sigma 1 and sigma 2 up top here. So we're using that same sigma 1 and sigma 2 right there to get our elemental force for the top material and our elemental force for the bottom material right there. So we have these same relationships right there, again, relating back to 4.25 and 4.26 in our textbooks right there. So this is equal to, we can plug in our relationship for our sigma 1, and we have our E1 over rho, which we saw from up top here, and for our elemental force 2 right here, we have our E2 y over rho right there from this relationship up top here from 4.24 right there. We can plug those in and get equations 4.25 and 4.26 relationships back to our textbook right there. But now we want to do this rather than doing this as a sigma 1 and sigma 2 right there. We want to do this with this shape, this new shape that we talked about down here in figure 4.20. So we take a look at this right here, and we can now see our centroid is right there on this guy with our neutral axis right there, our y-axis right there. So what we can do is we can use a relationship shown in equation 4.27. So dF2, our elemental force 2, is equal to negative, now this n value right there, so there's that n value by whatever shape change that is there, times our epsilon 1 times our y value over rho times dA. So we can rearrange that slightly, and what we can see here is this is equal to our negative epsilon 1 times y value over rho times n dA right there. Now from that, what we plug in for n is this ratio right here between epsilon 1, or sorry, E1 and E2, modular elasticity 2, material 2, modular elasticity of material 1, and that's how we get that geometry right there. That's how we get that value for the shape and dimensions of the lower portion when we convert this to something similar based on that ratio between the two modular elasticity right there to get that n value that we're going to use there. So the n value applies not only to the overall shape, but to the elemental shape right there is n times our dA right there, and that plugs in and comes into play with equation 4.27. So now I want to take and apply this to a conceptual application right here. So we'll look at concept application 4.3. And from that, we can have our figure shown here in 4.2AA. We have a sandwich composite structure right here. So we take a look at the cross section of that sandwich composite structure right here. What information they give us? Well, we got brass and brass on the outside of our sandwich right there. And in the middle, we got our steel. So we got steel sandwiched between two pieces of brass right there. All of them have the same length. They're all 3 inches long right there. But we can see that now we have 0.4 inches is the thickness for our brass on either side, and the thickness of our steel in the center is 0.75 inches right there. So what does it tell us in the problem statement for this right here, for this application? Well, the bar is made of bonded pieces of steel, and it gives us our modular elasticity. There it is right there. For steel, our E value for steel, that's our subscript right there, our S right there, is 29 times 10 to the 6 psi. And for our brass, our E sub B for brass right there is 15 times 10 to the 6 psi. They're both in psi right there, so now we have our modular elasticity values for both types of materials within this composite structure sandwich right here. So what do they want us to find? They want us to determine the max stress in the steel and in the brass when our moment, so they give us our moment right here, of 40 kip inch seconds is going to be applied. So with that information from our given diagram and from our problem statement, what we would normally do now is create our setup page for this here. So we go through, write out absolutely everything, all of our values, all of our dimensions, all of our units, how it relates back to our physical problem with our variable names and indices there, and create that there. And then from that information, we take a look at, this is what I'm given, this is what they're asking me to solve for, what are the assumptions I'm going to make, and from our assumptions we're going to make, we can begin looking for our solution. So here's our procedure for analysis for our solution right here. So just as we did in the previous slide, what we want to do is change our geometry. So we want to transform the bar to an equivalent cross-section made entirely of brass. So rather than having brass and steel, we're going to do one new geometry right there for a cross-section that's entirely made of brass. Then we're going to go ahead and evaluate the cross-sectional properties of this transformed section. Then from there, we can go ahead and find our governing equation in order to calculate that maximum stress right there, because that's what they go back to our problem statement here. They ask us to find the maximum stress right there in the transform section. This is the correct maximum stress for the brass pieces of the bar. Then once we've done that, we can move on and determine the maximum stress in the steel portion of the bar. We can do this by multiplying the maximum stress for the transform section by that ratio of our modular elasticity, which they've given us right there. So we saw that in our previous slide. So now we can get that ratio though. So if we find it for brass, we can get it for steel by simply multiplying that by that ratio of the modulus of elasticity. So now that we've had the opportunity to read through that problem statement, understand everything they've given us, everything they want us to solve for, look at those geometries, understand that composite sandwich construction, and then come up with that procedure for analysis. Now what we can do is we can find those governing equations based on all that information that we can reference back to and figure out where to begin our solution. So that's where that procedure for analysis that we came up with is going to really help us figure out what steps to do, in which order we're going to do them in. So the first thing we said we're going to do was we wanted to transform the bar to an equivalent cross section that's made entirely of brass. So rather than our initial diagram over here, we had brass, steel, and brass right there. We want it to be an all brass equivalent cross section right there. So as we mentioned in our procedure for analysis, and we saw on the previous slides within this module here, what we're going to need to do is come up with this value for n. So n is that ratio between the elastic modulus. So we take a look at that. Well, we have our steel over our brass. So we can say n is equal to E sub s over E sub b, where those were given to us in the problem statement. Our E sub s was given to us as 29 times 10 to the 6 psi. Divide that by 15 times 10 to the 6 psi. Gives us a value now for n, that ratio right there, of 1.93. So with that value there, and we see that's unitless there because our PSI cancels our PSI there. So what we want to do now is we go back to our initial diagram that we had from our problem statement here. Well, our brass was 0.4 inches on either side. Well, that's not going to change because we're making everything brass. So what is going to change is the equivalent thickness right here. We're going to multiply this value right here by our n to make our steel in a brass equivalent right there for our diagram right there for that equivalent cross section right there. So we take and say, okay, well, our new thickness right here is going to be our B sub t right there, our whole brass section right there, thickness is going to be equal to, well, the two brass sections aren't going to change right there. So it's 0.4 and 0.4. We can leave that the same. What is going to change is we multiply this 0.75 by this 1.93, and that's where we have this relationship there. We multiply that together right there. That's a 1.45 right there. So we say 0.4 plus a 1.45 plus 0.4 gives us a B sub t of 2.25 inches. And that's what we have down here in this diagram over here. Now that we've drawn this out, our height doesn't change. This is still 3. This is now 2.25. And our center section has gone from 0.75 multiplied by our value for n, and this is now 1.45. So now we've seen from our previous governing equations, we have a equation, a relationship here for calculating the maximum stress. And that's our sigma sub m is equal to mc over I, which then we realize is we need a value for I. Well, we have this right here for a rectangular shape now, and we have this nu, which is our equivalent cross-sectional rectangular shape right here. So this I for rectangular shape is 1/12 bt, where this is our bt that we're going to plug in right there, times that height, which we know for this here, cubed. This is equal to 1/12 now. Our B sub t we just found was 2.25. We can plug that in. Our h value is 3. That's cubed right there. So we have now is an I value of 5.063 inches to the fourth. Double check. Do your unit analysis out. Does this make sense? Yes, it should be to the fourth power right there. So now we have a value for I that we can plug in down here in order to calculate that maximum stress, which is what they'd asked us to solve for in that problem right there. Well, they gave us an M value in the problem statement that was 40 kip inches right there, and they gave us a value for C, which is going to be half our height, because our neutral axis, now that we've done that composite cross-sectional area, is going to be at 1.5, or half that 3 inches. So we plug our 1.5 in there. Now we have this value that we can bring down in here for our I value, which is 5.063 inches to the fourth right there. And now we do out our math right here, and we can find that our maximum stress right there is going to be our 11.85 KSI. Now what we said before as we were going through this in our module right here, well, this, for the material we're dealing with, brass, our maximum stress for brass is going to be equal to that sigma max right there. So that is that right there. But now for our steel, our max stress for our steel right here, this is going to be equal to that value of n that we solved for up top here from this relationship, or the ratio of our elastic modulus, times our sigma m right there. So we multiply our 1.93 by that 11.85 KSI right there, and what we find out is now that our sigma for steel, our maximum stress for the steel, is 2.29 KSI, and for the brass, it's simply our sigma M right there from this relationship here of 11.85. So this is what they'd asked us to solve for in that problem, and this is how we go about doing that geometry, finding our N value, and actually applying it to get that equivalent cross-section area, then plugging into our general equation for maximum stress, and we get these values out here in the end for both the brass and the steel. So now I want to take a look at a practical application for these composite beams right here. So one that we see, that I've seen a lot in the research and work that I've done, is reinforced concrete beams. So you see this a lot in bridge decks where we have these concrete beams that are going to be reinforced by steel rods or rebar in the bridges right there. So you have something that you see like here in figure A right here. We have that reinforced concrete with a cross-sectional area that we're seeing right here, showing that reinforced rebar steel right down at the bottom of that there, those 3 points there. And we have a depth from the rebar to the top surface up there. So these concrete beams are going to be subjected to bending. And in order to deal with that there, it's going to be reinforced with these rebar and the steel rods. So what the purpose of the steel rods is, they're going to carry the entire tensile load below the natural surface there. So as we saw, concrete is not great in tension. It's great in compression, but not so much in tension. So in order to deal with the tension, that's why we use these rebar to reinforce it to carry that load. So the upper part of the concrete beam still carries a compressive load, whereas the bottom part is going to the bottom part is going to carry the tensile load, which is why we have the rebar contained in that bottom section. If you think of this thing bending up like this, what's going to happen to the top of it right there, as we get to the top of it right there, what we're going to see is that's going to go into compression. The whole top section is going into compression, whereas all the elements in the bottom section are going to go into tension there, and concrete doesn't deal well in tension. You see that just crack and fall right apart. So if we're going to do that for a 3-point bending like that, which you typically see on a bridge as a car drives over, it's going to bend down like that, compress the top layer, put the bottom layer in tension. We put these rebar strategic places right there. Now in reality, this is a simplified version of this. There's multiple layers of rebar, and you got to think, because it's also wide. It's not just 1D. You have multiple dimensions of a concrete bridge deck. So this is more of a girder situation right here, rather than entire bridge deck where you have it running crisscrossed over top of each other at different layers for rebar if you're dealing with an actual concrete bridge deck there. So just a side note to make it more realistic for future applications there when we're actually putting rebar on the bridges. So with that, let's talk about now, this is going to be a transform section. So how do we deal with this in terms of an analytical hand solution to this here? Well, it's very complicated with that rebar in there, but we can do just like we did in our previous example problem there and do a transform cross-section area of this for the steel right there, replaced by that relationship there for our N value, where our N is that ratio of our modular elasticity of the steel over the concrete right there. So E sub S for steel, E sub C for concrete right there. So what we want to do with that there is we want to determine the location of our neutral axis. So we can come back over here and take a look at B right here. This is our transform section of all the concrete right there, and we can see we have this relationship. There's our B, our thickness right there. There's this height X right there, which is our distance off of that C value for our neutral axis right there. And we can see this value going up to the centroid of that top section of concrete right there is going to be 1/2 this value of axis right in the middle of this right here. It's the center of that right there. And this distance from the neutral axis down here to our NAS right here for the concrete in the bottom there is going to be D minus X right there, where D is that total length from the distance from the rebar to the top surface of that right there, minus the value for X right there. So that would be the difference right there to get this distance right there, like that. So with those variables, we can do to determine that location of this neutral axis right there. What we can do is we can say B times X, so that width right there times the height of that top section of the concrete right there, which is down to that neutral axis right there, times X over 2, which is that distance to the centroid of that right there, minus N, which is that ratio between our elastic moduli right there, times A sub S, which is the area of the steel right there, times D minus X, where D is that total length over here, and again, X is that distance for the top section of the concrete there, is equal to 0 right there, which now leads us to a simplified solution. We bring this out, bring the 1/2 out front, and then we have our X squared, because we have an X times X right there, plus our NAS, multiply this through and distribute it right there, X minus NAS D right there. So that's just distributing through and simplifying that to come up with our equation 4.28 in our textbook. So for a little bit more detailed information how to derive this with these variables right there, I reference you back to this section for 4.28 in our textbook right there. And we can see right here what we can do from this now is go to part C right here. We're looking for these stresses right there. And the normal stress from our governing equation for the concrete and the steel together to go to part C right here is given by sigma sub x is equal to our negative moment of y over I right there. So we can see that our C sub y, our sigma sub C is equal to our sigma sub x, and our sigma sub S is equal to n times the sigma x. So our stress in the concrete is equal to that stress in the x direction there for the whole piece right there. And again, just like we did in the other composite one, now if we gotta go back to steel, it's not the whole thing made of concrete like we're looking at in part C right here. We want to go back to steel. Well, that's that n factor there, that ratio between our modulus of elasticity right there multiplied by that sigma x value right there. So that's how we get our stress in our concrete and our stress in our steel for a reinforced concrete B. So now let's go through an actual example problem dealing with exactly that, concrete structure with rebar in it. So what we have here is a floor slab right here, simplified floor slab made of concrete, which is reinforced with, now they tell us more information about the actual reinforcement material, our rebar right there. These are 5-inch diameter steel rods placed 1.5 inches above the lower face of the slab and spaced 6 inches on center apart. The modulus of elasticity is given to us as 29 times 10 to the 6 psi for the steel, and for our concrete, the modulus of elasticity is given to us as 3.6 times 10 to the 6 psi for the concrete. Now, with applied bending moment, so they're telling us what that applied bending moment is, which could be the equivalent of something being loaded during the day, equipment sitting on it, people standing on it, whatever that may be. They tell us that is 40 kip per inch right there for a 1 foot width of the slab. So that's just that 1/5. They're giving us just one small section of this that we're dealing with here. And what they ask us to do now is determine that max stress in the concrete. So similar to that application we saw, but now we're going to apply some values for this practical application here. So we're going to look at this here. Here's our diagram up here so we can see the whole slab thickness is 5.5 inches. We can see that these are tells us in the problem statement that these rebar are 1.5 inches off the ground there, which would make this 4. So 5.5 minus 1.5 gives us as 4 inches from the height right there, which is really what we're concerned about right there. We can see there's our applied moment over there, and there's our 6-inch spacing on center for these 1, 2, 3, 4, 5 different rebar that are placed right there. And again, we have the diameter of those rebar of 5/8 inch diameter right there. So from this here, we create our setup page if we're doing our hand solution to this here. What are we given? What are they asking us to solve for? Write out the 4 things, our variable name with the indices, our numerical value for it. Then after our numerical value, we want that to be our units for that there. Double check for the unit analysis. And the 4th thing is how it physically relates back to our specific application right there. So that's how we'd write out our given section. We'd write out fine what they're asking us to solve for, and then any assumptions that we're making as well. From that, our next step is to think this through, and rather than just thinking it through in our mind right here, what we've been getting the practice of is writing these out for our procedure for analysis. So that's what I've done right here for our solution right here, is we write out that procedure for analysis. We want to transform to a section made entirely of concrete. So not concrete and steel, but just all concrete. Find the stress in the concrete, then multiply by that n value to get back and find our stress for the steel. So we already got a plan of attack with that there. We've seen a couple different example problems as we've gone through this module. From there, we're going to evaluate the geometric properties of the transform section, and then once we've done that for the geometric properties of the transform section right there, we're going to go back and calculate the max stress for the concrete and then back to the steel using that n factor right there, which is the ratio of our modulus of elasticity between those two. So now that we've had that opportunity to read through the problem statement, create our setup page, write down all of our given information, create a procedure for analysis in order to answer what they're asked us to solve for on the problem, what we want to do now is create a diagram right here, transforming the section into something that's made, an entire section made of concrete right there. So what we want to do is the same thing we've done in our previous example problems. We want to get our dimensions associated with this too. So we have this figure up here, figure 1, which is the transform section, to calculate this neutral axis. So that's what we want to do, is calculate this neutral axis here. So the thing to think about is, how do we want to visualize this here? So the way that we're going to visualize this here in this figure, we're really going to have 2 of those rebar in this here, rather than all 5 of them there for this example right here for how to solve this. So with 2 of those there's 6 inches on center right there. So if there's 6 inches on center away from each other right there, therefore we're going to have, if we have 2 of those on there, it's going to be a total of 12 inches of width right there as we look at those 2 pieces of rebar. And we have this right here down shown below in figure 3 to calculate this here. You can see there's a rebar right there, there's a rebar right there. That's 6 inches right there between those. That's 3 inches there and 3 inches there like that. So 6 plus 3 plus 3 is 12. So that's how we're drawing this out and solving this problem right here. So that's just where we're getting the 12 inches from right there, and that's going to come into play in a little bit while we're calculating the area of the steel as well, because there's 2 rebar involved in this. So next thing we want to do is this whole height right here from the top surface of the concrete down to the rebar layer is 4 inches, which is at 5.5 of the total thickness minus the 1.5, which is the distance of the rebar off the base of this here. So then we can say, okay, for our top section of the concrete here down to our neutral axis, that's some distance x that we're going to have here for that distance x. So then the bottom part here down to the bottom of this to make this entire composite section of just the concrete now is 4 minus x, where 4 is that total height minus that height of just the top section there of x. So then we can have this information there. Now, in order to find out what this is down here for the area here, this is going to be our N, which is that ratio, again, now of our modulus of elasticity between the steel and the concrete right there, times the area of the steel. That's the cross-section of the steel. And remember, again, it's 2 rebar that we're dealing with that there. So in order to get this value, we'll come over to the right here, transform this to a section made entirely of concrete. So we're going to need that N value with the ratio of our modulus of elasticity right there. E of the steel over E of the concrete, modulus elasticity of the steel divided by modulus elasticity of the concrete. Those are both given to us in the problem statement. For steel is 29 times 10 to the 6 psi. For concrete is 3.6 times 10 to the 6 psi. We do our math there. We see our psi and psi, our units cancel out there. We're left with a unitless ratio right here. Our N is equal to 8.06. So then down here, to get this value, our N times our area right there, this is going to be our N value that we just solved for, the 8.06 right there, times our area of the steel. So now there's 2 concretes, which is 1/2 pi r squared for our area. So that's our 2 right there because there's 2 steel rods right there. Our diameter of this is equal to 5/8, so it's going to be 1/4 pi d squared right there for that there. So this is now pi over 4 times the diameter of a 5/8 inch times 2, because there's 2 of these guys down here, 1 and 2 right there for the steel rods going through it. We do out our math, our N times our A sub S right there ends up being 4.95 squared. So that's where this value of 4.95 squared comes from as we plug this in to our transform section in order to calculate that neutral axis. So as we continue on with our solution, what we want to do next is to evaluate the geometric properties of this transform section that we've created right up here in figure 1. So from this here, we can go back to our textbook to take a look in reference equation 4.28. In particular, we'll take a look at the top section of this here. We have bx times our x over 2 minus nas times d minus x, where we can see our b value right here relates right here to our b value right there, times x over 2 minus our nas. Our nas we've just solved for above here. This is 4.95 inches squared. This is now times our d minus x. Our d value, well, that's just right here. That's our 4 inches right there. Now we have one equation, one unknown. We need to solve for our x value there. We can do that, and x is equal to 1.45 inches. So now we know this value for our x right here. In turn, we also know what this 4 minus x is now that we have a value for x there. So next, what they'd ask us to solve for, we can go back to our setup page and say, okay, what did they actually ask us to solve for? Well, we want to find the maximum stress. We have a relationship for our maximum stress here that sigma is equal to mc over I. We want to look at this for concrete because we've transformed this to an all concrete equivalent right now. So this is m times c1 all over our I value right there. So now we're going to need a relationship for I right there. We can look this up in the back of our book right there, come up with a value for I. We have this governing equation right here to solve for I. So we have 1/3 our base times our height cubed right there, plus our AS times N times our value right here of 2.55 inches squared, which is equal to, now if we plug this right in right now, this is equal to 44.4 inches to the 4th. Do these units make sense? Yes, it should be in inches to the 4th. This does make sense. So just to clarify where this equation comes from right here, so we have 2 different things. This is our I value for the top section right up there, our diagram right here, and this is our I value for our bottom section down here, where this right here is our NAS right there. That's why we have that 4.95 inches right there. And where this 2.5 comes from, that's this distance right here. It's a 4 minus x. So say 4 minus this 1.45 for x, that is 2.55 there. So that's where we get this value here for our I value for this section right there. So again, we add those two together from the top and the bottom right there to get this I value right here of 44.4 inches to the fourth. So now we can come back down here to our maximum stress equation right here, plug values in where M was given to us in the problem statement is 40 kip inches. We now have the C value right here, the C1. Well, that is going to be the same as that 1.45 or our X inches right there. And then we have down here on the base our I value that we've just solved for right there. So this gives us our stress of the concrete right there of 1.306 KSI. Now, if we want to do this for our steel, we can simply take and multiply what we did in the first part by that value for N. So we can multiply 8.06 times that 40 times. Now the difference is now we're using a C2 right here rather than the C1 down there for this distance right there because we did these out separately. So that's 2.55, but the same I value right there. And we find that our sigma for the stress right there, our max stress for the steel is going to be equal to 18.52 KSI. So let's take a look here now at stress concentrations. So what we have here is we have two different diagrams. In figure 4.24 and 4.25, we're both looking at the stress concentration factors. So 4.24 is the stress concentration factors for flat bars with fillets undergoing pure bending, whereas 4.25 is the stress concentration factors for flat bars with grooves or notches undergoing pure bending. So you can see right here, here is that bar with the notches right there, and you can see those notches cut out right there, and you can see over here, here's the fillets, and they're both undergoing pure bending. You can see our moments on either end of this, M and M prime for both of these right here to know that it's going under pure bending. What we can also take a look at within these here is we can take a look at the dimension that he's given us here. So we have our value for D here, which is the dimension right here going across this right here, so that's our lowercase d. We have our uppercase d going across this bigger section right here. So this may be like one end of a dog bone specimen right here, so you have that width of the head, the gripping head right there, and down here you have the small section of the cross-sectional area right down here where the gauge length might be. So that's just a practical application there. And then you have right here this R value. And this is something that's important as we are designing dog bone specimens like that, because we want to get that radius right there, that fillet just right there, so that that is not a stress concentration area. So what we can use these charts for, if we take a look at 4.24, we can say, okay, if I know this ratio between my D and my D, right here, my capital D and my lowercase d right there, I can then come down here and figure out which of these curves I'm going to be on. So you can see that is our ratio there, from 3 down to 1.01 there. And we can also say, well, I've got my moments on this as well. So for our moments on this as well, we can keep that as a constant. And the last thing that we do is a little r over little d right there. So for wherever this moment is, for whatever problem we state there, we're really just concerned with the geometry, this little r right there, that fillet radius over this distance or this length right here of the gauge length right there to get that width right there. So put that in, that's our R over D. So that's down here on our x-axis right here for R over D. So if we know just off the geometry what our R over D and our D over D is, let's just say our D over D gives us a ratio of 1.01, and our R over D gave us a ratio here of 0.05. So then we go up to this curve right there. We go straight up this from 0.05 for R over D ratio till we hit that curve. Then we come across, we can get our K value or our stress concentration factor directly there. So it's approximately 1.25. So that's how we can utilize this based on the geometry of our specimens right here. But again, this is different. This is for a flat bar with fillets. This is for a flat bar with notches, both under this pure bending where again we're assuming this M is going to be a constant value they're giving us in the problem statement right there. So from that information right there, the stress concentrations may occur in the vicinity of points where the loads are applied, in the vicinity of the abrupt changes in the cross section. So that's why having these ratios just right there for these and getting these dimensions just right for that to minimize certain areas where we don't want those to occur. And what we can do is we can also calculate our max stress right here. So our max stress, or sigma M, is equal to that stress concentration factor now, that K value times this MC over I, which we've seen that before. So this is now where these charts can come in and we can kind of figure out our geometries based off of these charts, get it just about right. And this is great when we're talking about a design process, especially as we're making these test samples to maybe back out some material properties.